right, so we're looking at this same integral where we talked about that fundamental theorem of calculus doesn't help us here because we can't write down an antiderivative for this function. And so we're going back to the definition and thinking about Riemann sums. We looked at a couple of examples with rectangles, and what we're going to look at here is actually using some different shapes that maybe are a little bit better approximation than rectangles. So I just drew a couple of them here. But the basic idea is that I've got these shapes, and I'll draw in one more here, but the width of each of these is 1. I've got this set up so that this one goes from x equals 1 to x equals 2, so the width of that is 1. And I've just used points on the curve. So I have one point here at x equals 1, y equals negative 0.26 at one side. And then at the other side, I have x equals 2. Y is approximately negative 1.96. So I've used those 2 points. And then instead of forming a rectangle, I just drew a straight line to connect those. And although the actual curve is a curve and the straight line isn't exactly the same as the curve, the area of this is going to be a pretty good approximation for the area between the curve, the signed area between the curve and the x-axis. All right, so there's 2 pictures of them here. There's one above the x-axis and one below the x-axis, both with 1 in this direction. And then thinking about the area of that shape, that's a shape that you may or may not remember an area formula from geometry. But usually when you see them in geometry, they're drawn sort of horizontally, and they look like this maybe, with some different labels here. But that's a trapezoid. And we have trapezoids here, but they're just turned on their side, and one side is straight instead of being angled on both ends. One side is straight, and the other side is angled. So it's still a trapezoid, just turned on its side or upside down. And so if you remember the area formula for a trapezoid, awesome. If not, I'm going to write it down here for you. All right, so the area formula for a trapezoid is 1/2 times the height. So the height would be the perpendicular distance between these 2 parallel sides here. So I'm going to label that h, 1/2 times h. And then times the sum of what are called the 2 bases. So these are sometimes labeled B1 and B2, or sometimes the one on the bottom is B1 and the one on the top is B2. But times the sum of those 2 bases. So that's the area formula for a trapezoid, which you may not remember. But that's basically what we're going to do here is we're going to use trapezoids. I'm going to use 3 trapezoids. Of equal width. To approximate the value of this integral that we're after here. So I'm basically using this area formula for trapezoid here, but the B1 and B2, instead of necessarily being true height, those are going to be signed height. So my first trapezoid here, the h, remember that this one's turned on its side here, the h is 1, and then the B1 and the B2 would be the lengths of these 2 sides. And so from our table of values here, we can see the length of this one at x equals -1, the y value there is 1.74, and at x equals 0, the y value there is 2. So we've got a height of 2 there. So the area of that first trapezoid, we're going to have 1/2 times our height is 1 times the sum 1.74 plus 2. All right, so that's one trapezoid. All right, and then the next trapezoid, I didn't actually draw to start with here. It's a little bit strange looking and maybe not what you would normally think of as a trapezoid, because one of the points at one end of it is above the x-axis and the other point at the other end is below the x-axis. So it looks a little bit strange here. It almost looks like 2 triangles, but my width is still 1, and I'm just going to connect these 2 points with a straight line. And so that looks a little bit strange. I've got this little piece here. That looks a little bit strange and maybe not like your typical trapezoid that you would think of, but the area formula is the same. And I'm just going to use my y values at each endpoint. So 2 on the left end of that trapezoid and negative 0.26 on the other side. And then the third trapezoid here, 1/2 times the height is 1. And then the sum of the B1 and the B2 will have negative 0.26 plus negative 1.96. Okay, so we just go ahead and do all of this addition. You might notice that I could actually factor out this. If I'm going to use equal width trapezoids, I'm going to have this 1/2 times the width of my partition here, so 1/2 delta x, and then I have the sum of all these things. So sometimes you'll see a formula for trapezoidal rule where it's written out a little bit differently, basically where they've factored some things out and combined some of these terms here in the middle. And it's fine if you want to memorize that formula, you can use that. Or you can remember the area formula for a trapezoid and then just do each one separately. I'm going to go ahead and write down what this would be in that form if you factored out the 1/2 times the delta x. So 1/2 times 1. And then if I look at what's left, when I factor out this 1/2 that is times 1 of all these things, I'm going to have my 1.74, and then 2 of these, 2 times 2. And then I also have 2 of these terms, 2 of these negative 0.26 terms. And then just 1 of the negative 1.96 terms. All right, so this looks a lot like the formula that you might see in your book for trapezoidal rule. It'll have 1/2 delta x, or sometimes they'll write that as delta x over 2. And then they'll have a y value. They usually call that y sub 0. That's the y value at the left end. And then plus 2 times the next y value, because I have 2 of them, one from each of the 2 trapezoids that meets up at that value there. 2 times the next y value, and then 2 times the next one again. So 2 times all of these middle ones, because you'll have 2 trapezoids that meet at each side, and then just plus the last y value here, so plus y3. So this looks like the formula that you might see in your textbook. And so you can get the same answer by using this formula, just remembering you'll have these extra factors of 2 on these middle ones because of the 2 trapezoids that meet up. Or you can remember the formula for area of a trapezoid, but one way or the other you need to be able to remember a formula to do this. So whether I do these calculations all separately and add them up, or I do it in this form, we're going to get an answer here. I think you should get about 1.63. And so that is a pretty good approximation for the signed area that would represent the value of this integral. So we used what's called trapezoidal rule here, 3 trapezoids of equal width. And we'll look at some other videos where we use another rule called Simpson's rule. And then we'll look at some examples where we talk about error bounds and how we might know how far off our estimate should be. Looking at the picture, you can see that it's not exactly 1.63, but we can see that that's probably pretty close to that signed area of that region. And we can think about how we might be able to estimate how far off we expect our answer to be.